Hello, everyone. Thank you for coming to our talk. So we're going to be talking about a little bit about DAGs today, but we're especially going to focus on a little abstraction that we built at work called Pacer. So, oh, thank you. So before we get started, hi, everyone. I'm Zack. I am a human who develops software at Cars.com.
I am Stephanie, and I am also human and develop software at Cars.com as well. And we're hiring, so come join us. And our amazing people that are up front, come talk to one of us or use our QR code.
All right, so before we jump into the talk today, I just want to give everybody kind of the lay of the land. Where are we going from here? So we're going to start with some really awesome news for you all. We have an orientation. Yay, it's going to be so fun. And then we're going to get our hands dirty with some pretty messy code. Then we'll jump very briefly into a DAG good idea, and then we'll talk a little bit, very, very briefly, and very high level about graphs. And then we're going to get into the meat of our talk today, which is about this little small abstraction that we made called Pacer. All right, so good news, everyone. Yay, you're hired at our new startup called XYZ E-Commerce. Woo!
Congrats.
Congratulations.
We're happy to have you.
Are going to be great engineers here. It's going to be fun. So welcome to day one. This is your orientation. So we're going to get you started off with some refactoring work. It's going to be great.
Don't worry, we'll walk you through the basics. It's going to be fine.
All right, so here we go. We have this one page on the site. A few points about it. It's a heavily trafficked page. It gets about millions of users per day. No big deal. There's multiple teams that work on different aspects of it, and they share a lot of data dependencies in order to get that page rendered for the users. And it's a really important revenue generator for the business. Like, all of the money comes from there, so no big deal, no pressure. It's going to be fine.
Yeah. We have some other things to mention. Maybe some cons here. Most of our production incidents come from this. Time for resolution, pretty high. Everything's in a private function, a live view module, and it's really hard to test. Instrumentation and observability, not really granular enough to figure out what's going on quickly. It's fine.
Yeah, but don't worry, you all are Elixir experts after all. It's going to be fine.
We can solve this problem.
Okay, so we're going to start small, okay? Let's put some bounds around what we would like you to do on this first day, or your first week. So we have this large private function that takes 8 arguments, as any sane private function does. And we want to refactor it so we get a couple things. One, we want to be able to simplify testing of critical code paths in that what is now currently this large private function. And we want to get instrumentation and metrics on a much more granular level than we have right now. We want to be able to monitor latencies. We want to be able to monitor error rates. And then we want to move team-specific data access, manipulation, fetching, all the fun stuff that you do with data on a web page, and move that into kind of saner single responsibility modules.
Let's talk about what's currently going on in this function. We start with a bunch of raw search results from our search engine. Seems simple.
Yeah, and then we get a bunch of stuff happens, right? Like on web pages all the time. You get user teams, they have to check in your logged in status, do all that fun stuff with users.
Makes sense. And then we enrich it. We decide if you're an identified user or not.
And then advertising team, they get some data that depends on the user team, and then they give you, good ads.
Ads are important, and then if it meets certain criteria, like you're born on a Tuesday, the advertising team makes a call to a third-party API to give you better ads.
And then we have an SEO team, because we've got to make Google happy, and they depend on all this data from the advertising and user teams and a bunch of different conditionals and stuff. Don't worry about it, it'll be fine.
It's fine. Oh, and there's also a products team. They also want to enrich the data for different users, give them specific results.
And then there's an analytics team, finally, and they just do filtering. They mess with the data a lot, and then sometimes they ship it over here, sometimes they ship it over there. That's not important.
Yeah, don't worry about that.
You'll figure it out.
Yeah. And there's a lot more, but you'll catch on.
It's so simple. It's so simple, right?
Yeah, it's fine.
Yeah.
It's fine. We definitely don't look like that.
All right, so let's dig in. Why don't we dig in? All right, so we have this big, 8-argument private function. There's a bunch of local variables and just madness happening inside of this thing. That's OK. That happens. So I have a proposal.
OK.
OK. I'm gonna take a hack at refactoring this thing. Okay.
That sounds great.
Why don't we use this idea called the token pattern?
What's a token pattern?
Great question. I'm very glad that you asked that because I happen to make a slide about that very topic.
I'm really happy.
Yeah, as it turns out.
Cool.
So the token pattern, as Elixir developers, you're all probably used to seeing this in one form or the other, but you can think of a token as usually a struct. It's a wrapper struct that's going to contain a lot of the data that you might need to do a single thing. So you can think of it generally as a single struct, but it could be a map or any other compound data structure. It could be a tuple, it could be a list, anything like that. And so you take this single data structure, you pipe it through a bunch of functions, and you could make it work really nicely with the pipeline operator.
Sounds better than just one private function.
It should be a little bit nicer, I think. So I think you're all kind of familiar with this, right? Plug.con is kind of an example of this. You can think of ecto queries the same way when you're piping queries through all the different things like where's ordered by, all that stuff. Depending on your HTTP library, maybe you see this with the HTTP requests and things like that.
Cool.
All right, so OK, I just spent 5 minutes, and now I'm done. So I made this token called a search results struct, and it just contains all the data that we need. And then
Nice.
I wrote all these functions, and now it's very nice. Simple.
Seems very simple.
Yeah.
Done.
All right.
Ship it off.
Prod. See you, everyone.
Bye.
Oh, goodness.
Shoot.
Well, that's not really what I had in mind.
That's not really better than what we were doing before. So let's talk about how we got here. Production incident 761. Make that channel. Make that retro. Advertising team has a new requirement. They need some more data from SEO, and they thought it was already available when we initiated that struct on line 1. So unfortunately, when we called personalized page, function clause errors, and our testing didn't catch it. So that's not great.
OK, well, I mean, this is super simple, right? This is an easy fix.
Yeah,
They just needed
totally.
to get data that wasn't there when they made their function call.
Yeah.
Well, we just make a new function and just throw it in the pipeline.
Yeah.
And then just
that's easy.
You can get the data in there.
Yeah. Done. Oh, wait. Products team has come on board. They have a new requirement. We want to enrich some data. Uh-oh. They want to make an API call. Advertising makes an API call. So now we have 2 API calls in a row. They need some data from the user team. So we put that in a place that makes sense. We learned our lesson. So easy. Let's put a new function. Done. Wait. Advertising team wants to get on that data now. So now we have third-party call, another call. But we learned our lesson. Put it after the products call. So we're good. We're fine.
Yeah,
right?
Looks good to me.
Yeah.
Oh, yikes. OK.
Wow.
762. Wow, this is like the 40th incident this month.
Yeah, that's
Wild.
That's not good.
All right. Well, OK, let's take a step back here. We'll have a little retro. What happened in this case? So as we mentioned, there's a couple API calls. And as we know as engineers, networks are generally reliable, and they never go down. Everything is fine most of the time. But on this day, unfortunately, the team or the API that the products team was relying on was having a bad day, as APIs do every once in a while.
Yeah.
And our P95 response times are 95%. The slow distribution, the slow end of the distribution, response times for our users went way over 2 seconds, and that's not great. We have these objectives in place, and we went above that, triggered an incident, and then we have to come in and do something.
Not great. I think we can fix that, though. We work in Elixir. We know about parallelization. So let's just make a parallelized calls. Let's make those 2 API calls at the same time. Simple, right? Done. Look at that.
So
Put some
easy.
timeouts on it. We fixed the problem.
All right, OK, but let's take a step back here, right? So we started with this simple pipeline, and then it started growing more and more. And is this actually better than what we had before?
I mean, sort of. but not really.
Yeah, I mean, so okay, we got a few things out of it, right? So we actually did have our teams go create single responsibility modules, which means that now they can test their things a little bit easier. They know the shape of the data that's coming in. They know what it looks like. They can write simple, I get this input, I get this output test. It's pretty straightforward. And then we have kind of clear ownership, or better ownership of all that code that was happening in that big private function now.
Yeah.
Kind of delegated out to teams specifically. So that's nice.
But we still have some cons here. We still have the teams that need to be aware of all the data points that all of the other teams are happening, right? So we saw the advertising team and the products team and the SEO team. They're all on different teams. They have to know what everyone's doing, and that's not really possible. And the pipeline's changing constantly. We always want to be enriching data. We always want to be showing something else. And then parallelizing high latency functions. This can go wrong really fast, right? What if we put two API calls and one of them relies on another? Blows up. And then, of course, connaissance of execution. When everything relies on another, you have to know what happens first. And that's, again, all teams need to be aware of. So that doesn't really solve that complexity problem.
Intriguing. Intriguing.
Yeah.
Wait a minute. I have a dag good idea. Maybe. I don't know.
Let's talk about it.
Let's talk about this.
Okay.
All right. So thinking about our problem here, we keep running into these kind of issues, right? Because we have all these different teams that are depending on each other for a bunch of different data points.
Yeah, and if the interdependencies between the data points, it's really difficult to wrap your head around, and we can't expect all the teams to know that, right?
Right. And if you think about it, so if you want to add something new to the pipeline, and you're depending on another team for data, you might have to move their function around too.
Yeah, and when you add a new call, it kind of requires you to know what's going on at all the times. And like if you want a new third-party API call, you need to know what the other third-party API calls are doing. That's a lot of problems, right? Like we don't know.
Yeah. I mean, like it's even more sinister than that, right? Because if you have, you're making an API call, but another team is depending on you, your API calls result to make their API call, and then there's other teams that are depending on the results of their API call, and then you move your thing down here, then you have to move all the other things all the way down here, and then who knows what's going to happen.
It's a web of dependencies. Also, you look like that meme.
Yeah, it's a Charlie's mind, spirit animal.
Yeah.
Anyway, but so if we take a step back, okay, this must be a solved problem, right?
It has to be. We need to know explicitly state what the dependencies are in the ordering of the function calls. And then we just need to have an abstraction, right? Like, this has to happen. There has to be a data structure that does this for us.
Well, I guess, I'm racking my brain on, computer science-y type things, but you've ever heard of dependency graphs before? That's a thing, right? Maybe we should look into those.
Yeah, I think Mix uses it, right? For their Mix EXX files, and then mixsteps.git does this for us. So how do they do it?
Oh, of course, right? When you do your mix dependencies, right? Mix will even check for you to make sure that, you don't have dependency A that depends on dependency B that depends on dependency A, because then you keep trying to fetch the same things over and over again. That doesn't make sense. That sounds like something that we probably want, right? Like if we think about our problem as like, oh, this team depends on me, and I depend on them, and I depend on them to do a thing, and then you just keep making function calls in a circle, it's probably not good in production.
Yeah, probably going to cause production incident 764, or 3, or whatever we're on now, right? So let's see. I think there's a couple different types of graphs. There's cyclic and acyclic, directed, undirected. We should probably use an acyclic graph and probably directed, right?
Oh, right. Yeah, okay. This is all coming back to me now. DAGs. That's an acronym for Directed Acyclic Graph.
Oh, that's what it means.
Maybe we could just go and then remodel this whole entire problem as a DAG, and then build an abstraction on top of it that will decide what is the best ordering of these function calls for us.
I mean, that makes sense, but that seems like a lot of work. We should probably talk to an expert first. Let's get some advice.
Okay.
Right?
All right. Okay, so we ran this by Jose. Generally a pretty smart human.
Yeah, I think we can trust his opinion.
And he said, yeah, maybe that's a dag good idea.
Cool.
Let's do this.
Let's do it.
Okay, all right. So before we get into our library explanation, we're gonna take a quick foray into the world of graphs. This is gonna be very, very cursory. We're not gonna get into anything deep at all, but just enough to cover some of the underlying concepts that we're using. All right, so in the world of graphs, so generally you'll have an acyclic and cyclic graphs. So if you look on the right-hand side, there's a cyclic graph, meaning that there's a cycle, right? If you look at the nodes B, C, E, and D, they're all pointing around at each other, kind of like the Spider-Man pointing at each other kind of thing. That's directed, or sorry, not directed, it's cyclic. These graphs are all directed, right? There's arrows pointing one direction. In an acyclic graph, acyclic, meaning there's no cycles, it's the only difference. We're going to focus mainly only on acyclic graphs. We don't want cyclic graphs.
Makes sense. Let's talk about a common thing, topological sort, aka top sorting. This was solved in 1962, so let's not reinvent the problem. There's a great paper written by Kahn, Topological Sorting of Large Networks. Highly recommend that. There's many algorithms that do this. We focused on Kahn's algorithm. There's usually an algorithm that does dependencies. One task depends on another. You can schedule it. It's just an execution of scheduling sequence. You might have heard of digraph, which is in Erlang, and in Elixir, there is a package called LibGraph. Both have different topological sorting implementations and the option to use other algorithms here.
Yeah, and so in the real world, you can probably come across this. A lot of you are probably familiar. Erlang already has built-in the digraph module for working with graphs. Elixir has a hex package called LibGraph that does a lot of the same things using kind of just a different data structure on graphs. And then, in the real world, we use this every day. When you call mixdeps.git, mixdeps.git is actually building out a graph and then running a top sort on your dependencies. You can see this also in something like Obon workflows.
Cool, so let's build a DAG. Let's take a very contrived example. 4 tasks that you need to do: loading the dishwasher, running the dishwasher, washing the dishes, and frying the steak. What do you need to do first? Washing the dishes. You need a clean pan. So before you fry the steak, you need to wash the dishes. But also, you need to load the dishwasher and run the dishwasher after you wash the dishes. So let's take those dependencies and make a visualization of a graph. So here we go, easy. Washing the dishes, top node. Then we're going to fry the steak on the side. But then we got to go back and load the dishwasher and run the dishwasher. So this is what a DAG looks like. This is a directed acyclic graph. However, if you see this, there's a very obvious problem here. We can do 2 things at once. So how do we do that? How do we do 2 things at once?
Introducing Pacer. Woo!
Woo!
Oh, it didn't. Our
didn't do
sound
the
effect didn't work.
Hold on. There
Yes.
we go.
Thank you, Daniel from Say.
Yeah.
All right, so we created this thing called Pacer at work, and basically it relies on some of the concepts that we just talked about from the world of graphs. So really, this is a very small abstraction / library, and there's one main module in there called Pacer.Workflow that is the core abstraction, and it will give gives you superpowers to some of your structs, which we'll soon see. So your first question probably is, how do I use this thing? How do I use Pacer? And the answer is there's a couple parts that you need to know at a high level. Use the Pacer.Workflow macro in your modules. That will create a struct for you, very much like an ecto schema. And you can define what we call a graph with a couple fields, right? So in this one, this is very contrived, very small. There's only 2 fields. There's a field called wand. There's a field called magic. You can see that the magic field has a couple things tied to it. One is a resolver, which tells it how it can produce the actual value that goes under that field. And then it declares explicitly its data dependencies within that same graph. So in this case, our magic field is depending on the wand field having some data that's present that it could use. And then that the resolver function is going to take in a map of all the dependencies. So for the magic field, it's going to take in a map with a single key wand and then whatever the value of the wand field is. And then you just call pacer.execute. So you could give it a struct, an instance of the struct, or you could just pass in the module itself. And then what you get back is just a populated struct or map. So given this kind of contrived workflow that we have with just 2 fields, if you look at the resolver function, you get the wand, that's your dependency for the magic field, and then we just interpolate that into a string, right? You have used the magic, whatever the value of wand is. In this case, we're passing a struct where the wand value is set to super wand, And then you get that back. And at the end, you get the struct magic, where the magic field is now set to you have used a super magic one. It's just magic.
Magic. All right. So now that we've introduced you to it, let's go over some key concepts and terminology, what we have the options to do.
So workflows, they're intended to manage, to help you manage complex workflows. So for the example that we just saw with 2 fields, you probably don't need this. This is more intended for things where you have maybe dozens, hundreds, even thousands of data points where there's interdependencies between the data points that are available there. So a workflow is just a set of data points or fields where the fields declare the dependencies on the other data points in that same graph, and they do that explicitly. At runtime, they're just plain old structs. All the graph stuff that we just talked about, that all happens at compile time. So fields have to define a one-arity resolver that takes in all of the dependencies that that field declared that they had dependencies on, and then you can do whatever you want in the resolver functions. There's also some capabilities we'll talk about of how you can take a bunch of fields resolvers and then run them in parallel.
Cool. So the main thing that we wanted to do is have some compile time safety guarantees, right? We want to make sure all of the fields are there and have values and rely on each other, and we know what's going on. So we can detect and prevent cyclic and reflexive dependencies. So field A and field B can't rely on each other. We have some field checks, so we can't have duplicates. We can't have dependencies on fields that don't exist in the workflow. We have batch checks, so we can prevent invalid batches. We can't have fields that have resolver functions defined that resolve within the same batch. You can only have one workflow per module. You can have as many workflows as you want, just one per module. The resolver contract is strong. It has to be a one-arity function that takes in a map. And we tried to make the errors formatted well and very clear about what you need, and examples of like cyclic dependencies, dependencies not in the graph, et cetera.
Yeah, there's some other benefits to this too. So we wanted to prevent a whole class of problems that you could run into if you had invalid, basically graphs defined, so like cyclic graphs or something like that, that would end up, you would have resolvers calling resolvers and never have that in. We didn't want that to happen. So that's why we really focus on the compile time checks here. We run the top sort algorithm, the topological sort algorithm, build your graph out. That all happens at compile time, as I mentioned. So we're offloading, the CPU and memory overhead load to do that at compile time, and then basically just caching the results of the top sort on whatever graphs that you have. And then just the other benefit, right, it just gives you a centralized repository of fields. If you have a really complex workflow, you can just go look at the docs for that and see what all fields it defines.
Makes sense.
Some downsides of this, right? So because it does do some work at compile time, that means that if you have lots of these things, it can potentially slow down your builds a little bit. And then also you cannot dynamically add or remove fields at runtime.
All right, let's talk about what a field is. It's just similar to an ectoschema. It's just a one-to-one key in your workflow struct. So field 1 is a key, field 2 a key. In our visualization, if you think back to that example of the DAG, it's just a node in the graph. So real simple. We have some options on fields. If they have a dependency, they have to have a resolver. Remember, the resolver is a one-arity function that takes in a map. The dependencies will default to an empty map or an empty list if you don't define them. And then defining a default is also an option. So if you see in field 2, we define a default.
All right, so resolvers are the other key piece of the puzzle here. So if you think about fields as the what, resolvers are the how. They're one-arity functions, as we mentioned before. They take the input, which is all the dependencies that you declared, and then they return a value. It could be any arbitrary value, and that gets placed on that key for that field at the end of the workflow running. As I mentioned, it's always called with a map. And then if you declare any dependencies in your field, we do require that you define a resolver. All right, so a simple example of what that looks like. So you have another simple workflow here. You have field 1. It doesn't have any dependencies, so we're assuming that you have some data in memory that you want to use to populate that struct. And then the dependent field depends on field 1, and it calls out to that resolve function. I have a typo in the IOInspect call. It should be IOInspect inputs.field1 because there's no such thing as field 1 value. But anyway, so at the end of the day, this workflow runs, and the value of dependent field is going to be exactly equal to the value of whatever is in field 1.
Cool. So batching, this is the main reason that we wrote this. Parallel field resolution. This is what we want when you have big high latency resolving calls, something that hits the network. This is what we need. So you can't have dependencies on fields that are in the same batch for obvious reasons. It's parallelized. It has to be a unique name within the workflow. You can have many batches, but they each have to have a unique name. They all have to have resolvers, obviously. And then ordering of the fields doesn't matter within the batch because it's parallelized. And then we have some options for you on timeout. We default to kill task, and then the timeout on it is defaulted to 1,000 milliseconds for each batch. So let's go back to our example graph of washing the dishes, loading the dishwasher, running the dishwasher, frying the steak. So obviously, we want to do two things at once. We want to do loading the dishwasher and frying the steak at the same time. So how would we do this in our Pacer graph? So we're going to define some fields. Washing the dishes doesn't depend on anything. Running the dishwasher depends on loading the dishwasher. We have a batch defined with 2 fields in it, frying the steak and loading the dishwasher. Each of them has a resolver. Each of them depends on washing the dishes, which is good. They don't depend on something else in the batch. And we have defaults defined because you have to have a default in a batch field. So pretty simple, very contrived. This is what our graph looks like now. Very easy, right? Now we have just 3 nodes, washing the dishes, then the batch where it does that parallelized tasks, and then running the dishwasher. So I think we've solved that problem now.
Cool, cool. Okay, and so now we'll get into a few just other options that we have in certain use cases. So some more advanced use cases that we have. You don't always, if you define a set of things that you want to run in parallel, in some cases conditionally, maybe you don't actually want to make that API call depending on what some other data looks like in your workflow. And in order to be able to skip that, we came up with this idea of guards that work essentially like the normal guards that you see day to day, right? Like with a when, return a Boolean. If you return a Boolean, you end up, either doing the thing or not doing the thing. So for us, guards work only on batches. You can define a one-arity function. It takes in your dependency map, and then if you return true, we will spin up an extra task and then run whatever that resolver is supposed to do. If it returns false, we just skip that altogether and return some default value. And then, so important to us, because we actually did have some big workflows with a lot of teams working together, that we provided some documentation, right? Because we want to make sure that users who have important fields can kind of state some background context about what that field is, what it's intended for, where the data comes from, and that kind of thing. And then we also generate module docs for you automatically. You can opt out of this if you want to, but by default, it's just going to take all your fields and say, here's your list of fields in your Pacer workflow, and then we'll also say, these things depend on all these things, and if you have a default set up, it will also list out your defaults.
All right, let's talk about virtual fields. Something that we ran into was you need a field to use to calculate another resolver, but you don't care about it in the end, right? So we added this option. It's defaulted to false. You can do virtual true, and as you can see here in our resolver for field 2, we use field 3. But since it's virtual true, it's not used in the result of execute. So we do Pacer.execute on that workflow. We have field 1 and field 3, and then we get field 1 and field 2 back. So you're saving some memory overhead there of not carrying those values downstream.
All right, and the last thing, so we added telemetry on 2 different levels here. So with our workflows, we wanted to have like a full wrapper. How long does it actually take for you to run your workflows? And so there's telemetry around that. We do a start, stop, exception event around the Pacer workflow execution in its entirety. So use cases for this would just be, creating dashboards for latencies on important workflows to you, being able to monitor, things like error rates on the workflows as a whole. And then we did the same for resolvers. So every time a resolver actually gets invoked, there's some telemetry that gets emitted around that. So start, stop, exception events on each resolver's execution. And we provide you with the field and the workflow so you can actually look at what field's resolver was running when such and such happened, or an exception happened, or something along those lines. And then, so we actually use this to build out dashboards on things like success and failure rates on really granular levels for specific data fields, and then to monitor latencies across those resolvers. This is an example of like a dashboard that we did build in real life to measure error rates and things like that. So if something starts to go wrong, or we have a deployment, we can see automatically when these error rates tick up, and we could see exactly what function that it's pointing at to help us kind of ward off any issues.
All right, and then something that's not really important to the logic of Pacer, but something that's, I think, pretty impactful is the visualizations built in. So if you want to visualize your graph, visualization.visualize, which is really hard to say. So it takes in your module in an optional path, or it just writes it to the root of your project with a stringified version of your digraph. And then you can use your favorite visualization tool, we like Graph is, to do that. And we will show you an example of what we actually use Pacer for. That's what our graph looks like.
So simple.
So that's
simple.
why we built this. So no one should have to know that. Oh.
Come on, Daniel.
Come on. There we go.
Okay, all right.
So yeah, we've open sourced this. You can find it at the GitHub. We have some hex docs for it. We'd love some input, anything you think would be better. Yeah.
Awesome. That's all. Thank you.
That's it. Thanks.